Everybody, hope my previous video entertained you. That was on 3rd July, related to the design of impellers used for cooling towers. So that particular episode uh, tells more about the design aspects of an impeller, the induced draft fan impeller, and how that is installed under the cooling tower, and what exactly are the conditions, the boundary conditions, the rotational velocity imparted by the shaft onto the impeller, and how much hot air and the noxious air is being lifted from the uh, bottom environment to the top. So that was the simulation uh, in the previous episode. I also gave you uh, a good understanding about how the system can be modified. So, which means like what are the advantages of using a plane strain system, an axisymmetrical system, and a surface model, and then a solid model. Okay, so we discussed all these four aspects, and based on that, a simulation was performed. The analysis was done. The stresses, the strains, and the deflection, the deformations were observed, and based on that, we also, discussed a bit about the fatigue and the durability of the system, the shaft, and the shroud, the disc shroud. So today we are going to focus on yet another type of simulation. That is when the entire system is involved. Say, for example, the previous uh, simulation we discussed about the impeller. Impeller is just a system. You know, it is a system which comprises of a shaft, okay, and the rotating end, and there is a power transmission. The power transmission is done through the shaft, and the shaft rotates. The shaft also rotates the shroud, and along with which the impeller rotates. Okay, so there are some bearings, and with the bearings. So what we have done is we have reduced the complete system, and we have just taken a single system called impeller. We did the analysis, the simulation of that, and we found out the stress, strain, deformations, fatigue, durability, etc. Now, let us imagine a situation where you also need to understand, from where the power is getting transmitted. Let us say there is a motor, okay, there is a prime mover, and from the prime mover, there is the power transmission which happens onto the, which is getting transferred to the shaft, and from the shaft it is getting transferred to the impeller, that is the disc shroud and the connected system. So this will be treated as a complete system. This is no more a subsystem, because this involves both impeller, the shaft, as well as the prime mover, the motor. Now, such situations are very difficult for simulation because it's a very time consuming simulation, because we have three different systems, okay, three different subsystems, and all subsystems combined together to form a single system. And this single system will be comprising of more than, say, about 600, 700 parts easily. Now, the question comes, individually analyzing a part and analyzing a complete system. There is a big difference. There is a lot of time consumption. There is also a lot of process methodology involved in simulating it. So what happens is, as a single body or a single part, we can understand what is the constraint mechanisms, and we can also understand how the loads are getting transmitted. Okay, so in a single subsystem, it's possible. Likewise, how we performed the simulation on an impeller. Now, let us imagine the motor connected to the shaft, and the shaft connected to the central disc shroud. Now, central disc shroud is connected to the shaft with bolts. So there will be nuts and bolts connected together, which will be about some 30 mm dia, 8 numbers of, say about 16 numbers of, 28 mm dia. So like that, you have a lot of nuts and bolts, and these nuts and bolts are connecting the impeller to the shaft, that is the disc hub, and then from the hub to the shaft, and the shaft is getting connected to the prime mover. Okay, so there is a lot of uh, contacts, which means the impeller is connected to the disc shaft. So the connection is with the nuts and bolts. And from the disc shaft, it is getting connected to the shaft hub. Okay, and from the shaft hub to the shaft, and the shaft to the prime mover. So what happens is there is the connection, individual connection between these entities. Okay, so which means there is a surface of one body is meeting with the surface of the other body. Okay, so there are mates. One surface is mating with the other surface. Okay, so now these surfaces are regions where the kind of, the mechanism flow happens. The mechanism flow happens from one connection to the other connection, one contact to the other contact. Okay, so that has to be defined. Now we know that the motor rotates. So when the motor rotates, there is a rotary force, and this rotary force is generating, a circular motion on the shaft. So a circular motion is nothing but a circular force, and this circular force is creating, a circumferential velocity, and this circumferential velocity is rotating your impeller. Okay, so now this circumferential velocity is what we call the rotational velocity. And this rotational velocity has to be given, has to be imparted onto the hub, the disk, the shroud disk. Okay, so now we have to assume that it is getting transferred from the shaft. Okay, and from the shaft, it gets transferred to the disk shroud. Okay, so what we do is we connect, we bolt the system, we bolt the system, and bolting the system, what happens is, we are releasing the rotation of that particular axis. So there are 6 degrees of freedom, 3 in the translation and 3 in the rotations. So we call it as Tx, Ty, Tz, Rx, Ry, Rz. So now which axis the bolts are, so that axis it is released. So there is a rotation. Okay, there is a free rotation which is imparted onto the shroud. And now we apply the rotational velocity exactly at the center of gravity of the system. So that is the impeller system. Because the impeller center of gravity and the total assembly center of gravity, there could be, variation. There will be a variation. If suppose the shaft dimensions or the geometry changes, the disk hub geometry changes. If it is not symmetrical, okay, in many conditions, there will be a change in the center of gravity. So we cannot apply it at the center of gravity of the system. We will have to apply the rotational velocity at the center of gravity or the rotational center of the impeller. Okay, so now we know there are multiple connections. Connection between the impeller and the hub, the disc shaft, and then from the disc shaft to the hub, from the hub to the shaft, and from the shaft to the prime mover. Okay, so what we do is we select the surfaces between these two geometries, and then we define the contact. So once we know that what are the contact parameters, because there will be a rolling friction, there will be a kinetic friction, there will be a static friction. So friction is a very important parameter. Now we need to define what is the frictional parameter. So there could be, a change in material also. The disc shroud of the impeller will be, it could be a MS material. Okay, the hub of the shaft could be a stainless steel material. The shaft itself can be a alloy, okay, alloy steel. Okay, so different materials can also come into picture. Now, the coefficient of friction between one material to the other material, okay, it varies. Okay, so definitely we need to assume the actual parameters, the actual physics. So which means that these two surfaces are in contact and there are some contact frictions, and because of those contact frictions there will be some resistance and some stresses, stress accumulations because of that. Okay, so this entire thing we need to uh, impart perfectly onto the system, the complete system. Okay, so earlier it used to be a subsystem where only impeller came into picture. So now we have three different subsystems, and all subsystems put together for a for the complete body, that is for the complete system, assembly system we are going to perform. So when we perform a simulation for that, okay, there are two ways of doing it. One is if we only need to know the forces, the reaction forces, etc., the normal forces, then we can go for the multi-body dynamic, that is the kinematic simulation. So there is a practice, there is a process called kinematics, and in kinematics we really don't, we don't need to do the what do you call, go for finite elements. Okay, so in kinematics, we call it as rigid body, and we need to find out the rigid body motions, and then we try to classify it into static bodies and rotating bodies. Okay, or moving body, translational bodies. So based on that, we apply the parameter. So we apply a motor, okay, towards the end of the shaft, and we assume, okay, a single line as a shaft, and we can probably give some dimensions to it, and then we can connect the impeller, and the impeller can be considered as a mass. Okay, a small box or something like that, or a circular, a cylindrical body with a mass at the center of gravity exactly equal to the mass of the impeller. So this is how we try to break the system, and this breaking the system and defining it in terms of the inertia, moment of inertia. Okay, and then the loadings are applied at the center of gravity of the structure. So this is how the kinematic simulations are. So that will be a rigid body system. Okay, so now based on this, we'll be able to get some understanding. Say more mainly, this is adopted in places where we need to uh, create an input for a bigger simulation. Say for example, when we are supposed to perform a dynamic simulation of a skid assembly or a turbine assembly, what we do is we need to create a power spectral density. We need to get some inputs from the basic system, that is the basic dynamic systems. So that we call it as a rigid body simulation. We perform a rigid body simulation, and then I mean, the kinematics, and then we take a input from that, the power spectral density, accelerations, etc. Now, this power spectral density will be the input for the higher analysis, like for harmonic simulations or for random response simulations. Okay, so those are high-end simulations where we, we uh, we are supposed to be finding complex, what do you call, solutions. Say, for example, when there is what do you call, a shock load. A shock load is imparted onto a system. There is a jerk. A car is moving on a road, and suddenly there is a pothole. The car jumps, or it dips onto the pothole, and because of that there is an enormous amount of shock load, and this shock load hits the chassis, and from the chassis it gets transferred to the seating system, and from the seating system it goes to the human, that is the occupant. Okay, and there will be, there could be a possibility that the occupant can shift or move or drift from the seat. Now sometimes there is a possibility that the occupant may not be wearing a seat belt. Okay, so just because of this jerk, there is a possibility that the occupant can lift and his head can go and hit the roof, or his forehead can go and hit the glass, or his face can go and hit the steering car or the steering system, steering wheel. Okay, now in order to design and develop the occupant restraints, your seat belts, the airbag deployment systems, and all, these kind of analysis are very important. And these are very complex. The time taken for performing a crash analysis, a frontal impact, or a side impact, or a roof crash. Okay, all these things are very complex. Now, in order to perform complex systems, as I told you, in finite elements, it will take days together. It used to be taking days together. Now, at least it will take hours together because so many number of equations, so many number of unknowns. Okay, so now it has to solve using a proper algorithm, and then it has to give you the results. Now, in order to make these kind of complex simulations simple, we go for kinematic simulations or multi-body simulations. So we have tools, like MSc Adams that can perform your kinematic simulations, so multi-body simulations. We have tools like Recurve, that is again a multi-body simulation tool. So likewise, you have many commercial tools available in the market. But what I want to, mention here is about why we use that kinematic simulation or when we use the kinematic simulation. Okay, so now here I told you that the complete impeller assembly has to be simulated. Why? Because the impeller is going to be placed onto a system. Okay, the impeller has to be kept on a pedestal, and this pedestal has to be, very properly conditioned. I mean, the leveling has to be done properly. There should not be any parallaxity. Okay, it has to be kept evenly parallel to the ground level. So there is a lot of, tolerances involved in designing the pedestal. So the pedestal is just not a PCC flooring or a structure. Okay, it is a reinforced system. It is a reinforced system where it has got anchor bolts, and these anchor bolts are connected to the impeller. Okay, and it is ensured that there is 100%. There is absolutely no shock loads. Which gets into the system. So they have neoprene dampers connected. So every anchor bolt will have a neoprene damper, and these neoprene dampers are shock absorbers, and they will be able to resist the shock load because these shock loads are repetitive. Okay, when the shaft rotates, let us say about 1000 rpm, say 1000 rpm, then a variable 1200 rpm, then slowly 1500 rpm. Okay, then again 1800 rpm, then 2000 rpm, then again slowly it reduces. So there is a cyclic loading which is involved. The RPM keeps increasing, then again decrease, then again increase. So what happens is when there are repetitive loadings or impact loadings or these kind of sharp loadings coming on the structure, this has to be completely eliminated from the structure. That is, from the impeller assembly, it has to be eliminated. It has to be, transferred into the pedestal and then to the ground. So this is how every designer is supposed to be designing the complete system. Okay, so now how multi-body dynamics or simulation is going to help. Now, in multi-body dynamics, there is a possibility that we can make a certain body of our interest as flexible. So, which means that out of all the 10 rigid bodies, out of the all rigid systems, okay, the interest of our, the area of interest is impeller. And now on the impeller, there is a specific, disc shroud, that is the area. So because of the complete total load from the prime mover, what are the shear loads which is coming on the plates? That is our question. Now, in order to do this, if we perform complete finite element analysis for the entire system using individual contacts, okay, that's going to be a nightmare because we won't be able to complete the simulation. There could be, there could be a possibility where the equations are not going to converge. There won't be any convergence. It keeps on diverging, then it creates an error and it comes out of it. It will give you some kind of, socket error. It won't be able to, complete the simulation. Okay, so in such situations, it is preferable to go for multi-body dynamics, as I mentioned. So this is what they do in every industry, even in the aircraft industry, for the complete flutter analysis or the flutter simulation, or a bird hit simulation, okay, or any aerothermal simulation. The entire structure, the complete structure, the aircraft structure will be treated as a rigid system, and then any one system or any particular part, is what do you call, converted into flexible body, and then on that flexible body, the simulation is performed. Now let us say that there is a bird which is entering the jet stream. So the aircraft is, propelling forward at some speed. Okay, and then there is a bird which comes in the opposite direction that gets sucked into the blades. Okay, so there is a cowling, and within the cowling you have the rotor blades, the sail blade, the complete gas turbine is fixed inside that. That is the jet engine. And now when the bird is sucked by the air inside, it goes and hits these blades. The entire system crashes. The complete aircraft, the engine can burn off. Why? The reason, because it's impulsive. Okay, the bird is going to be treated as a fluid which is kept under pressure. It's a fluid action. It cannot be, it is no more a solid body. It will be like a fluid, a blob of a fluid, a high viscous blob, goes and strikes on the solid system. Okay, the system crashes. It will be like, a crash analysis. There is a car which comes, or a truck which comes in the opposite direction, it goes and hits, the vehicle, the car. What happens? The front bumper to the dashboard, everything goes off. And sometimes it can even become, it can even go beyond a certain case where the, fatality can also happen. The passengers, the driver, everybody can, perish. I mean, they collapse just because of the frontal impact. Okay, so this we call it as impact dynamics. Okay, we call it as impact dynamics. Now, such complex systems when we need to perform the complete, the finite element simulation of the complete system is a nightmare, an impossible, not an impossible thing. It could be done, provided you have, yeah, these days you have GPUs. Definitely we can do, but the solution time for convergence and all will be very high. Okay, so multi-body dynamics is a system which is adapted for performing these kind of simulations. Okay, this is true. Now let us imagine a simulation, a dam, that is the water from the reservoir which is stagnated on one end. Okay, and the gates of the dams are open. The water rushes out from the stagnated end to the other end. That is, from the source it goes to the sink. So at that point of time, there is a huge splash of water from the top to the bottom. So that's the top main, I mean, MSL, and the bottom there is a MSL. So from the top to the bottom, there is going to be a huge amount of splash, water that is going to come. So quantity of water discharged from all those openings, Q is equal to A into V. So Q1 is equal to A1 V1, Q2 is equal to A2 V2, Q3 is equal to A3 V3. Like that, you'll have 10 or 15 shutters. And now from each shutters, each area, there is a certain, a velocity with which the water is going to flow. Okay, now assume all this water is going to come and hit to the penstock, I mean the bottom area where the turbines are kept. Okay, that is going to be a huge load. Okay, huge dead loads. Now the entire dam system, the penstock systems, the other, the mechanisms or the other structures connected to that are all have to be designed and designed for the ultimate loads. Getting it? So which means the factor of safety of these systems are going to be very high. It won't be like how we design aircraft or how we design cars and all. It is not going to be kept very lean, say 1.5 to 2.3 like that. These factor of safeties are going to be huge, maybe in terms of 6, 7, 8. So earlier, those days it used to be kept like that, 13, 15. That used to be the kind of factor of safety. But today it is reduced. But still, they have a certain, ratio. So they keep it as either 3 or 5 or 12 like that, depending upon the structures. Now this simulation cannot be done using our structural simulations, I mean the dynamics and all. These are called special simulations. Okay, we generally call it as fluid structure interaction, FSI. Fluids and structures combined together. It's a fluid structure interaction. Even the previous system, previous thing what I told you, the bird going and hitting the engine, the aircraft engine. That is again a FSI. Okay. Now this FSI, the fluid structure interaction problem, is a bit tricky. Okay, and similarly, let us say that there is a oil tanker, and this oil tanker is transporting oil, or say it could be a highly inflammable system, any highly inflammable system from one part of the country to the other part of the country, and there's a huge distance, and the roads are going to be not even. So there are conditions where the roads are going to be really bad. Now the tanker has to withstand all those criterions, and now we need to understand one thing, that there is a possibility for this highly inflammable or a corrosive system, the liquid, to catch fire also because of friction, internal friction. There will be a slosh, like a fluid sloshing, which means that the oil tanker is moving, at the same time the fluid is also moving. The fluid will move in the opposite direction because of some restitution, energy, inertial, kickback. Okay, there will be a slosh, and these slosh can trigger, okay, fire. There is a possibility that the slosh itself can trigger fire. So one layer of the fluid to the other layer of the fluid, there will be a friction. Okay, and there can be a friction between the fluid and the structure. Okay, so in order to reduce this, the tanker has to be designed in a different way. It cannot be an open tanker. The tanker need to have baffles kept at some specific distance. Baffle from top to bottom, baffles from bottom to the top. Okay, and then it should be in a similar, it should be a situation where the fluid, the kinetic energy of the fluid is broken. It's it's completely broken down into different uh, pieces. Now, only when you are, able to change this, you are able to break this particular energy. Okay, the what do you call, the frictional force can be avoided, and just because of the the frictional force, avoiding the frictional force, okay, the inflammable capacity that can be reduced, which means that the flaming capacity will come down. Okay, so. Uh, I told you about the benefits of using multi-body simulation, the higher order simulations, and all those things. I also gave you an example about an aircraft. I gave you an example about the crash analysis of a car, of a vehicle. I also give you a example about the oil tanker, etc. So apart from this, there are very big applications, very huge applications, especially in geotechnical engineering and tunnel engineering and coastal hydraulics, etc. Okay. So now, I just gave you a few examples. Okay, and I also showed you like what are the kind of analysis or the simulations which is used in these uh, case studies, these kind of situations. Getting it? Now, there are some specific softwares, special purpose softwares, which is designed alone for this. As I told you, Ricardan is specifically for tracked vehicle simulations and multi-body systems, etc. You have MADIMO, Mathematical Dynamic Modeling. That's again a software, a product. Okay, and I used to be working for that company called TNO Automotive Safety Systems. And we, in fact, developed that tool called Mathematical Dynamic Modeling. And this is extensively used in all automotive and aerospace companies. Okay, and this completely works on rigid body simulation and XML coding. Okay, and this is specifically used by the industries where occupant restraints. They focus on occupant restraints. That is designing seat belts, airbags, etc. Okay, now uh, in the next session we will discuss about acoustics. That's again a very interesting part, and why I want to give you all these domain, some good understanding on all these domain is everything is from a single point of generation. That is force. Okay, a force is the reason. Okay, for everything. Say for example, in the seabed, there is a disturbance because of random movements of the tectonic plates. There are disturbance, and these disturbances come in the form of earthquakes, and it will further magnify and become tsunamis. Okay, now it is all from a single force, a point load. Okay, this entire system, the entire huge fleet of complex loads are getting simulated. Fine. So that is the reason for any simulation, structural simulation is the preliminary, the basics. Now from the structures, we we try to learn the complexities of the material, the complexities of the structures also, the geometrical structures. So that is the reason we go for normal mode simulation. Normal modes are eigenvectors. Now we need to understand like what are all the ways a structure can deflect, what are all the ways a structure can collapse, what are all the ways a car can twist. I mean, moving at a very high speed, suddenly, hitting a sledge or maybe an obstacle on the road or a pedestrian on the road. How the dynamics of the car changes because from one form of the load it completely deviates and then it takes a complex shape. Okay, so similarly, how the aircraft is able to lift, how the aircraft is able to move on the higher area. I mean, how it is able to fly on the higher areas, and how it is able to lift, and how it is able to stabilize on the upper atmosphere. Okay, so all these are all these are based on dynamics. Okay, these are called the dynamic systems, and all these are based on the dynamic loads acting on the structure. It can be flow, it can be thermal, because thermal is again a flow. Okay, movement of heat loads from one point to the other point, from the source to the sink. Those are thermodynamic systems. Now that is possible. It can travel from one point to the other point through convection. Okay, it can move from one point to the other point. Okay, you heat a rod, iron rod, from one end, it will transfer to the other end through conduction process. Okay, and there is air moving on that, and the air is also going to take that particular heat from one point to the other point. That is convection process. Okay, and in body kept at some specific distance apart, at a distance. Okay, the heat from this body is getting transferred to the heat, I mean to the other body. Now, how is this heat getting transferred? That is through radiation. So there are mediums. There are different kinds of mediums. Air is a medium. Water is a medium. Blood is a medium. If we perform, some neuromuscular simulation, okay, so we need to design the muscle tissues. Okay, we also need to design the blood. We also need to design the what do you call the bones. Now, in order to in order to simulate the complete neuromuscular skeletal simulation of a human body. Say, for example, somebody has gone through a very horrible accident, and then he is being admitted in the hospital, and then the doctors are working on him, operated, and multiple operations, multiple complex bone fractures. His skull has broken, his jaw, the bones have also crushed. Okay, and his collarbones are also broken badly. His ribs are all completely broken. Okay, and now many skull injuries also. Now the doctor needs to understand like what would be the kind of what do you call the implant that can be used if at all the patient is supposed to go through an implant analysis, surgery. And now the doctors have also need to decide whether there needs to be some artificial skin or tissue that needs to be generated in a special environment, and that has to be stuck onto his face. And now once it is stuck, okay, on the skull, okay, whether that particular tissue which is artificially generated or developed is able to have the same amount of tenacity, the elasticity as the actual muscles. Now, these kind of complex biomechanical simulations or systems can be done using these kind of softwares. Okay, so let me just wind up here for this session. Okay, please go through every statement. I mean, everything what I mentioned. You please go through this. This is going to be very useful for you. Okay, for making certain decisions. If you are engineers, practicing engineers. Okay, and again, as I mentioned earlier, please feel free to write to me. Please feel free to send your comments. I'll definitely respond whenever I have time. And I will also ensure that you are able to have some interactive sessions also. See, why I'm not able to make the interactive sessions, it is not that I don't want to make the interactive sessions. When I make the interactive sessions, there will be, a disturbance from what I speak and from what you listen. Because listening is more of graphics. Okay, people get carried over by the graphics. Now, when I speak something, you will be able to, understand that or hear that. So that's the reason I am going to give you the video sessions, the audio sessions now, and then the corresponding video sessions are also put. So you will be able to understand what is a flutter analysis. You will be able to understand what is a fluid dynamic simulation. You'll be able to understand what is a fluid structure interaction, what is a slosh simulation. You have all these videos. Just search for Baba Simlabs Private Limited. You will find all these simulations. Okay, so don't forget, please subscribe this channel and share as much as possible because uh, experienced people like me in the industry, from the industry, okay, you have very limited people who have the time to share this information. And I want to specifically share this information because I know that there is still a flaw in digital simulation. There is a flaw in computer aided engineering. Flaw in a sense, not the flaw in the system. I'm talking about the flaw in the process. People are not able to integrate it with their engineering properly. Okay, and now that is actually because they don't or they haven't properly understood the system. Okay, and that is the reason I am here to share my experiences, and I'm going to keep everything very simple. I'm going to make it simple. Okay, I'm going to verbally explain things which you are not able to understand. How a rigid beam element is, created, or what is a multi-point constraint, and how a multi-point constraint is useful in terms of transferring loads. And if you have multiple systems, and each system, how we are able to generate loads. So all these things are possible only when you understand the actual element theory, the actual process behind it. Okay, and I will try my every possible way to make it very legitimate, clear, so that your mental roadblocks are all opened up. Okay, So see you in the next episode. Till then, thank you very much. And this is Praveen Ramachandran Nair, the Chief Executive Officer of Vaava Simulabs Private Limited. And we are a drone manufacturing company, and we are in the process of manufacturing surveillance drones. We have agricultural drones, healthcare drones, and then drones for logistics and drones for fire extinguishing. And we are on the continuous improvement process, and we are also on the continuous research of advanced drones for various other applications. Okay, thank you very much.